pretty easy to see what's going on. Yes, we have vector x here with some components. We have the vector r here, the output of the layer, for example here R1. And basically each component of R1 depends on all components in X, yes? Because of this non-zero linear projections and application of some nonlinear function to each of the components. So basically each component here depends on all components before, and if we draw what depends on what, we have basically this, all these edges between components of X and components of R. Because of this, we call this fully connected. We can't add any other connection because we already draw all the possible connections here. So basic idea for this convolutional nanometer is to reduce the number of parameters some way, and also to reduce the number of connections. Because for images we feel that this number of connections is too big because of the nature of the image itself. So, let's see how to achieve these two goals. The first thing we can notice is that image is not a vector. It's a matrix. It has some two dimensions actually, yes. It will be, I take all these, so it should not be, that will be width and height. And also it can be additional channels. Here, typically for an image we have 3 channels. Red, the intensity of red color. Green, the intensity of green color. And blue, the intensity of blue color, the typical way to store an image in the computer. So we store this intensity separately, and if you combine both the channels into the image, you obtain something pretty close to you see what is very always. Okay, so we have this guy here, this is our X, and output we can suppose also should be of something of similar structure, yes? It can be of different widths, it can be of different height, it can have different number of channels, but still it is a tensor of this form. C1, for example. So, let us think about on what should depend each guy here. Also an image, and this H and W can be actually very in virtual mathematics. You can say that they are similar to H and W is the initial X. And basically we can say that this point would depend only on the neighborhood of this point in the original image X. And if you move further to the right, for example, we move to the right in dependence, so we have this receptive field for each point that is a local neighborhood in terms of indexes. So because of this, we have not all connections here, but only some subset of connections. And because of this, the number of parameters would be much smaller. For example, a typical local neighborhood would be something like 5 by 5. So it's our central point, and calculate some component ij is some minus 2 x I plus j plus l is the corresponding w notation ij
потом суммируют. Ну, короче, да, типа, они суммируются все сразу, а потом
Okay. Let's see what's going on here. So we have something is I and j is index of a specific parameter. Yes. So here this x has indexes 1, 1. It is x 1, 1, and this guy is x h w. And so we index all the points next. In the similar way, we have h 1, 1 and h w. And so we have also all indexes in between. We take a specific R here, R like ij, here, and draw a neighborhood on it. So basically, if you take k and l that equals to 0, this indexes would give us xij. So this is the exact same point, but before application of this transformation. And then we have, for example, k and l from -2 to 2. It means that we can take 2 steps to the right, 2 steps to the left, 2 steps top, and 2 steps bottom, and everything in between. So basically, we have all these numbers, and we multiply each input with the corresponding weight. Also, we can sum here the respect of the general number and obtain another solution.
Тема слов точно университет.
Yes. We don't need all the things. We need only, we don't need to define all the limits, we need only one limit here, and let's compute how many parameters we have. Let's call this neighborhood a filter. And now we have a filter size, k and l, and so the number of parameters in this guy here is 2k plus 1. No, k. Let the dimension to the filter it to be a square of size l. Then the number of elements in this matrix is l squared, and that's all. And we can, for each component in the matrix, we have the same number of parameters. So it is now the number of parameters at each layer. Basically, in all notation, it is l squared times d. So instead of d squared parameters for each layer, we now have l squared times d parameters. So it's much better than it was before, especially if this l squared is significantly smaller than d. And what else we can try to do to reduce the number of parameters even further? I would say that instead of l squared times d, we would have only l squared parameters. So now we have no dependence on the index of x. We know that our rj is all the sums x again I plus k j plus l c, and here you have delta k l c. So these parameters no longer depend on the position of the filter in the matrix. All the filters are the same.
Wasn't it before the same filters for all positions? So we have
Before that, we can say maybe we can have different positions, different positions.
the general case when we have different filters for.
Yes, this is a more general case. No one uses this, but okay. You can use it. Now we have the same filter for all the positions, and the number of parameters reduces to l squared because we need to define only single filter for all the matrix, and that's enough. And the total number of parameters in the network is k times l squared. Very good. What else we need to make it work? Actually, again, one example of a filter. Basically, two examples. One example, let it be this filter. This is the identity filter that does not change anything. Yes? So basically, we say that our xij equals to or rij equals to xij, because all the parameters equal to 0 except this one, and this one is 1. Another example of a filter is something like this. So all the numbers in this matrix equals each other. It's 1 divided by 9 for this filter 3 by 3. And basically we take the average over all this neighborhood. And okay, let's do some x plus a, j plus l, 1 divided by 9. So it is a smoothing filter, and you can apply actually the similar filter in your favorite tool for image transformation. Just smoothing of what you see, just reducing the resolution, but it's impossible. There are other filters that we know in computer vision for decades. Can you say, for example, some filters to sharpen the boundary between two parts of the image and so on. But what is different from this classic computer vision is that now we can learn all these filters. Similar to what we learned when we were doing backpropagation before, we learn all these parameters when we backpropagate and take the derivatives with respect to the parameters of this filter. And it is as easy as computing the derivatives for a common multi-layer fully connected neural network. So we benefit from all these optimizations. Also, to make it work for convolutions, we typically need few matrices. And I want to list some of them to make you understand better what is going on and why we need this. The first innovation, engineering innovation, is the replacement of this activation function with something simpler. Basically, the problem with this thing is the value of the derivative. If you draw the sigmoid function, g sigma of g, then you can notice the derivatives as this and as this part of this function is very close to 0. And it means that we have 0 derivatives, and this is what we propagate in our neural network. So we basically multiply by this derivative. When we go back, it is like this. And so when derivatives will be close to 0, and it means that when we take a gradient descent step, we modify our parameter value only at a tiny scale. And we need some nonlinear function that has bigger. So instead of which modern neural networks use something like so-called rectified linear limit. And this regular function of g equals to g if g is equal or greater than 0, or 0 otherwise. So if you plot this function, it would have the following form. Yes.
Is it differentiable?
Differentiable? Yes. At all points except 0.
So if it has no derivative at 0, how we can use it for optimization?
We don't care about 0. It's only a single point, so not quite much code. We have countless points where you have the derivative, and the derivative is 1 here and 0 here. And that's enough. The chances that we will be at exactly 0 is 0, and even if you aim 0, you can take the derivative between 1 and 0, what you would like. So, also, if you worry too much about this, you can try some generalizations. If you look a smooth one, for example, you can smooth this thing a bit near 0 and then to 0. Like if you scale up, in process, basically, let's close up this guy here and say what is going on here. Then we have parallel function. There's a form, and we have different variations of smooth rule that is 0 here, and then something that now close to linear function. In practice, I suppose both activation functions, this real rule and a variant of smooth rule, works pretty much the same. So actually no one bothers too much about this thing, because again there is only one point, this discontinuity of the derivative. And also this derivative is much cheaper to calculate, because okay, you just compare this t to 0, and if it is bigger than 0, then the derivative equals to 1. If not, then it is 0.
But actually, due to some instability in calculations, I think the probability that we have the 0 is very low. I mean that if we...
It's only a single point.
Yes, it's just a single point, 0, 0. But actually, if we have some, due to instability in calculations, the chance that we have 0, 0, I think very low.
Yes, it's low. Okay, so we don't care about it.
Yes. I mean,
it's not about instability. Again, we have the full range of these points, like full set of real numbers. And okay, formal changes to be in exactly 0 is 0. And to be in the neighborhood is also 0 because it is an infinite set. So if you don't care about this and use the abstract linear limit, this better derivative and easier to what else do we usually do to improve the behavior of all these guys? Basically, we need, if you are talking about multiple lectures, suppose we have key 50 layers, we need this derivative to be calculated well when we go back to the first layer. Because basically, we kind of calculate derivative step by step. So you start with the layer 50, then the layer 49, 48, and so on, up to 1. And it is a problem because the errors with the evaluation of the gradients accumulate, multiply by each other, and so on. So we need the derivatives to be pretty large. Sorry.
Bless you.
Thank you. So what we can do? Actually, we can try to artificially make the derivative close to what we want. And before we have some filter that we apply to x to get, and then some linearity like rule to get R1. So rule will be already modified. What we can do about this guy? Actually, the trick is very simple. It's called skip connection. So we just apply the filter and we add our old friend x to this filtered value. So basically we keep them as it is, and at each layer we have the following thing. This is a skip connection. And if you like figures, most of the people are thinking about it in this way. We have x, we have some filter f, a convolution to obtain r up, and then we go around this filter to say that r up equals to f of x, to know this called skip connection.
But what about the dimensionality of X? Does it have another size after the feature, and you wanna sum it up with the initial image?
Let's go back to, okay, basically, most of the times we need the same size before and after. Basically, we can have the same number of layers, or not layers, I'm sorry, 8 bits, and basically what we typically do in this convolutional layer is that we keep all the sizes, and also one comma here is supposed to have a point at the edge. Yes? And we are talking, if we are talking about the point as the edge, actually, that point at this point, we have a neighborhood like this that goes outside the initial image X. The more natural way to deal with this problem, to keep image size the same after the convolution, is to say, let's fill this part with some values. What values do you suggest? Zeros. Yes, it just says, let's draw additional zeros outside of this. And the size of this so-called padding preparation would equal to the size of the filter. Yes, error. To make it understandable. And because of this, we can keep the size of it. But if we continue these layers one by one, we will still keep the dimensionality of our problem and still would have a very large number of parameters in the very end. Because basically, when we end up with some R, K, and it is of the same dimensionality as the initial X, we actually benefit little. Because basically, to make predictions with probabilities, we typically apply one fully connected layer or two fully connected layers on top of this array. So we need to somehow reduce the dimensionality of R. And the idea is again as simple as this can be. Let's imagine, okay, let's define this another, so it was a skip connection idea. Another idea is called the introduction of